All right, more enzyme kinetics discussion. And sorry about that, flipped the slide too soon. So what we're looking at here is what's called an energy diagram. On the y-axis, we have the free energy of the reaction, or G. You might remember Gibbs free energy from Gen Chem 2. The x-axis, the reaction coordinate, which is the same thing as the progress of the reaction. And what we're looking at here is a reaction that is at equilibrium. When a reaction is at equilibrium, the energy of the reactants is the same as the energy of the products. So we have equilibrium here, and at equilibrium, the change in delta G, which is reflected here, is 0. So here we have the reactants, energy of the reactants. We have the transition state, so we have A, B, C. So this is the TS state, which is always at the peak of this curve or graph, and we have products here. Because the transition state is so short lived, they're not usually readily accessible to most analytical techniques. Thus, the transition state of many reactions can't be identified with absolute certainty, but there are some that, if their lifetime is long enough, can be detected. Typically, lifetimes are from 10 to the negative 14 to negative 10 to the 13 seconds. So just another characteristic of this diagram, this peak or this hill is what must be overcome before we can actually create products. Okay. Now we're going to look at the difference between a spontaneous reaction and a non-spontaneous reaction. So in nature, the free energies of reactants and products are seldom identical. So on the left, we have an energy diagram of a spontaneous reaction. So we have reactants going to products. Again, here's reactants. Here's the hill we have to climb, and here's our products. In spontaneous reactions, the products have lower energy than the reactants, and the delta G reflected here of this reaction is negative. So this is a thermodynamically favored reaction. But the height of that hill that has to be climbed determines how fast that reaction goes, or the rate of that reaction. And that's where the catalyst comes into play. It's going to lower the height of this hill. Okay. On the right, we have a non-spontaneous reaction. So let me take a step back here first. So this reaction is spontaneous in the forward direction. However, it is non-spontaneous in the reverse direction. Look at the hill it has to be climbed going in the reverse. So reverse, the reactants have higher products or higher energy than the products. So in other words, it's non-spontaneous. Same here. This is a non-spontaneous reaction. We have reactants, we have the hill we have to climb, and then we have the products. And the products have higher energy than the reactants in this process. Delta G here is positive. So negative delta G's correspond to spontaneous reactions, positive delta G's non-spontaneous reactions. This reaction would be spontaneous in the reverse direction. So what is the effect of a catalyst on this generic reaction? So we are looking at a spontaneous reaction here. Here are reactants, here are our products if we follow this red part of the diagram. So it is spontaneous, but when this is the uncatalyzed transition state, catalyzed transition state. So the hill has been lowered. The amount of energy required to reach that transition state is lowered. Thus, that means that the reaction speeds up and we have more molecules reacting that achieve the transition state per unit time and therefore increased product. So basically that catalyst decreases the activation energy. And I should say, note here that this delta G with the symbol beside it is the same as the energy of activation that is used to describe this variable in chemistry terms. Biologists or biochemists used delta G. There are certain functional groups in enzymes, the enzyme catalytic site, that perform the same catalytic function as small chemical catalysts do, and that of course is to stabilize that transition state. There are basically three catalytic mechanisms used by enzymes, and there are the first, acid-base catalysis, and this involves proton transfer between the enzyme and the substrate. So amino acids that can be involved in this type of catalysis are aspartic acid, glutamic acid, histidine, cysteine, tyrosine, and leucine. The second form or mechanism is covalent catalysis. And in this mechanism, a covalent bond forms between the catalyst or the enzyme and the substrate during the formation of that transition state. So this involves nucleophilic attacks. And then third are metal ions that mediate redox reaction. Almost 1/3 of all known enzymes are metalloenzymes, and that means that they require some sort of metal ion for their activity. Transition metals are the metals that are used by these metalloenzymes. So iron 2, iron 3, copper 2, manganese 2, or cobalt 2 are examples of metal ions that are involved in metallic enzyme catalysis. So we're going to look at reaction velocity in two different ways. On the left, we have a graph that shows reaction velocity on the y-axis, enzyme concentration on the x-axis, and as this reflects, the more enzyme present, the faster the reaction, and they are directly proportional to one another. Okay, so if we look at this graph, which is called a Michaelis-Menten graph, we have the reaction velocity plotted against substrate concentration. This is a hyperbolic curve. Where did we see that before? It looks like the myoglobin O2 binding curve. Okay. So the hyperbolic shape of this curve suggests that the enzyme physically combines with a substrate to form an ES complex, or enzyme substrate complex, which is what we have at that transition state. So as substrate concentration increases, initially the enzyme activity appears to increase linearly. However, this is less dramatic as substrate concentration increases, and at very high concentration it actually levels off, as we see here, as it approaches its maximum value. And that is when all the enzyme present is saturated with substrate. So I mentioned Michaelis-Menten as the name of that graph. And what that Michaelis-Menten is a theory, and it has an equation. For basically what it is a rate equation for enzyme catalyzed reactions. It assumes that there's a formation of an enzyme substrate complex, assumes that the ES complex is in rapid equilibrium with the free enzyme, So that is reflected right here in this equation. We have enzyme plus substrate. We have, we lost a little arrow there, but our K1, our equilibrium constant in the forward direction to produce the enzyme substrate complex, is in equilibrium with the reverse. So enzyme and substrate are coming together and freeing, okay? So there's rapid equilibrium. The breakdown of ES to form products is assumed to be slower than formation of ES and the breakdown of ES to reform ENS. Okay, so this is the K2. This is a slower process to reach enzyme, free enzyme, and the release of our product. Again, this is a Michaelis-Menten graph. We didn't look at what this graph can tell us or describe anything about this graph other than it is a hyperbolic curve. But what it tells us is a few things. So the Vmax basically is the enzyme's maximum velocity, or how fast the enzyme can work in converting S substrate to product when the enzyme is saturated. We can also determine a Km. So this is an equilibrium constant. And this constant, or this Km value, is the substrate concentration when Vmax is at 1/2 or 50% of 1/2 Vmax. Okay, so that's a substrate term. The lower the Km, or the smaller the Km, the greater the affinity that enzyme has for its substrate. And conversely, the higher the Km, the lesser the affinity that enzyme has for its substrate. We're going to take a look at this together in another short video, just momentarily, and we'll talk about these variables and how we can manipulate them or use them to get other information about our enzyme activity. But theoretically, Vmax is a constant, so maximum velocity. It's a constant, it's theoretical, so it's never actually achieved in reality, but we get very close. To reach Vmax, it would require that all the enzyme molecules be tightly bound with a substrate, so in that ES complex. And we know that there is an off and on equilibrium between enzyme and substrate. So Vmax is asymptotically approached as substrate is increased. The kinetic activator constant, so this is our Km. It is another constant, and it, like work in general chemistry, is derived from rate constants. So we can also derive that mathematically. Under true Michaelis-Menten conditions, an estimate of the dissociation constant of E from S is also reflected by the Km. And I've already told you a small Km, tight binding or high affinity, and a high Km or a large Km means weak binding or low affinity between that enzyme and substrate. So this is what's called the Lineweaver-Burke double reciprocal plot. Excuse me. In practice, it's difficult to accurately assign Vmax from the Michaelis-Menten graph. A better method is for determining Vmax, and Km uses this equation derived by Lineweaver and Burke. It's the double reciprocal plot, and what it gives us is a y equals mx plus b equation. So this can also be used to determine how enzymes are inhibited or shut off with respect to inhibition. But the y-axis here is 1 over velocity, the x-axis is 1 over substrate. And we're going to look at these together in more detail momentarily, so I'm not going to say much more about this graph right now. So other ways to describe or measure enzyme activity, kcat, the turnover number. So this is the number of substrate molecules converted to product per enzyme molecule per unit of time. So this basically is a measure of activity but also efficiency. And this also is when enzyme is saturated with substrate. So if the Michaelis-Menten model fits, K2 equals the kcat, which equals Vmax over E enzyme concentration total. So kcat, turnover number, equals Vmax divided by enzyme total. And that is an equation we will be using. So values for kcat range from less than 1 per second to millions per second. And another useful calculation is what's called the specificity constant, and we will be using this too. That is the kcat divided by the km, and that shows us or tells us how good the enzyme is and allows us to actually compare enzyme activity. So here's a table that gives some turnover numbers with respect to enzyme activity. Catalase, and this might be the enzyme that I asked you to look up, haven't decided yet. Oh, and the other thing I want to point out, this K, remember, it's a rate constant. First order, 1 over S. Okay. Catalase, 40 million, excuse me. I think I misspoke somewhere along the way with respect to a number. Anyway, forget I said that. 40 million. Penicillinase, 2,000. DNA polymerase 1, 15. That's kind of surprising because DNA polymerase 1 is used in replication of DNA. But guess it works well enough for us. Lastly here, we're looking at the ratio, as I mentioned a moment ago, kcat to the km, which gives us that specificity constant. This has units of a second order rate equation, 1 over m times s, so molarity times seconds. But again, this allows us actually to compare enzymes to enzymes or catalysts to one another, and we can see here the kcat. So at this point, we are going to take another break, and we are going to do some work together, take a look at some of these graphs more closely, and work some enzyme kinetic problems.